function. Looks like a logistic function. A synonym for logistic function is sigmoid function. But the output is given inputs x1 through xn. The output is this familiar logistic function of a weighted linear combination of the inputs, plus some other weight, just like logistic regression, right? But unlike logistic regression in neural networks, what we often do is put together a collection of these threshold units. And as we'll see later on in class, some neural networks, especially these days, depart from using this precise function. Now people are exploring all kinds of varieties of functions that define the individual units of a neural network. Some people use linear functions. Some people use these threshold logistic functions. Some people use simple linear functions that if they go negative, they just output a 0. And so there are all kinds of experimentation and research going on these days. But at least in the majority of cases, and for decades, this was the definition of neural nets. So we're going to start there, and we'll look at some of these alternatives later in class. So then, just like any function approximator, if I ask you to develop a machine learning algorithm to train it, you should think, well, maybe I should train it to maximize the likelihood of the data, that is, get maximum likelihood estimates of the parameters. What are the parameters? Oh, they're these weights. In fact, there's a set of weights for each unit in the network. So we can do that by minimizing the sum of squared errors in the network output. We can train it with map methods as well. And here's an example of a neural network. This one, these two nodes represent the inputs that represent a speech signal. In this case, these are frequency formants that capture the power two different parts of the power spectrum of a speech signal. And so that each point here is a speech data point. And these particular data points represent somebody speaking the vowel that you hear if I say head, hid, had, hod, hod, hoard, heed, hood, hood, hood. So those were all different vowel sounds. And each of those gives rise to different frequency components, and they're plotted here. Okay, so those are the inputs. That is, any one of those sounds, oo, would be represented as a vector of these two numbers. And each of these circles represents the output of one of the threshold units. So here's the threshold unit. It has two inputs, and it produces an output according to that logistic function. And you can think of these edges as representing the weights, W1 and W2, that are used to compute the output of that logistic function. And of course, as we know, logistic functions output a value from 0 to 1. And so then this value, which is going to be between 0 or 1, along with all of these values, become the input to a second layer of threshold units. For example, this one takes as input all of those intermediate values, and using its own logistic function with its own parameters associated with these edges, it outputs a number also between 0 and 1. Okay, so this is sort of like logistic functions of logistic functions. It's a way to think of it. Very weird, so it can give you very nonlinear functions. This network happens to be trained to identify which of those vowel sounds is being said when we capture these frequency components. And the way that that is encoded is when we train the network, we put a 0 on each one of those outputs, and we put a 1 just on the single output that corresponds to the vowel. Okay, so if I say U or I, then we'll make this one a 1, all the others 0. And so now we have a network that takes a vector as input and produces a vector as output. And we can try training it, which means train all the, there's a weight associated with each of these black lines. And when it is trained, then if we look at the decision surface that it learns, that's actually shown here. So the dots on here are the different data points correspond, and they're, if you have a really good vision, you can probably see that that's an open circle meaning heed, and that's a plus meaning hod. But the decision surface that's learned by this network, the function that it actually learns, carves this space up into these different regions where it, each region is defined by the set of points where the network, given that F1 and F2 input, will output one of these labels as its predictions. Okay, so like here's the region up here where it will predict heed, for example. Yeah?
Who would and put the sounds are same? So would they, both of them would be 1 or one of them would be 0.5, 0.5?
Well, maybe I'm not that good at saying vowels, but they're meant to be different sounds. Each one of them is meant to be a different sound.
So there can be only 1 in the upper row?
Yeah, the way your hearing works is that there's a range of different frequencies I can say, but you will hear them as the same sound. Is that answering your question?
There would be only 1 in the upper row.
Only, well, we train it with all zeros and a single 1. After it's trained, of course, the network can output any vector it wants. And so we decode it by saying whichever those output units has the highest value, that's the one we'll take. Okay. So then the output is really a continuous vector, and I'm discretizing it according to that classification rule to chop this region up. Thanks. Yeah, I should have said that. Yep.
It is like a combination of different linear separators.
It's not a combination of linear separators because it turns out a linear function of a linear function is a linear function. So there's no way that you can combine, if each of these is a linear function, there's no way you can compose linear functions to produce a linear function. And while it is true that logistic regression produces a linear decision surface, it produces a continuous output between 0 and 1. And so I think the way to understand why this is so nonlinear is to realize that the inputs here are real valued. These are also real valued. They're numbers between 0 and 1. And at this level, we do not pin those to 0 and 1. Whatever, this might be 0.7. And then that will be used as a 0.7 as the input to this next stage. So what we end up getting is a nonlinear function of a nonlinear function over continuous variables. And then when I apply my classification rule, which is to discretize that by picking the one with the largest output, then I get this nonlinear decision surface. And people have experimented with things like, well, what if these are linear units instead of logistic units? But if you think it through, linear functions of linear functions are linear functions, so it doesn't really buy you any additional benefit. Okay? But I like this example because it kind of captures very succinctly what a neural network, multi-layer network of sigmoid units, logistic is a synonym for sigmoid units, and the kind of very interesting nonlinear functions that can be classifiers that can be learned using these things. Okay. All right, so let's look at a couple other examples. This is one of my favorites because this is due to Dean Pomerleau, who used to be a PhD student here and later was a professor in the Robotics Institute here, and later started a company that builds devices that go on cars and buzz if you start drifting off the road. And for his PhD thesis, he built the first successful machine learning algorithm for driving cars. And he did it with a neural network. This was in the early 90s that he did this. But what he did was he put a camera pointing out the windshield of the car. You see it up on top. And that captured an image, a grayscale image, which he represented as a grid of 30 by 32 pixels, each having some real valued intensity. And then he made a neural network with each of those pixels as one of the input units. So it had 30 times 32 inputs, a small number of hidden units. People call these hidden because they're not observed values, they're calculated. Only 4 hidden units. And then he encoded as output the direction that the car should steer. And again, he has a vector output with 30 units, but the way he encoded it was with a kind of thermometer. Or actually, the most successful was a Gaussian peak. So he would make all these zeros, but if you should steer, say, this direction, this means left, this means right, this means straight ahead. If you should steer this direction, he'd make this a 1, and he'd make these like 0.5, and then all the other zeros. So that was his encoding, and it worked very well. He took the state of the art from the point where people were messing around out on Flagstaff Hill and trying to get the car to drive 10 miles an hour without driving into a tree. And he got it to the point where his car was driving on Route 28. I don't know if any of you have tried to drive on Route 28. It's very scary. But on a light traffic Sunday morning, he had his car driving 55 miles an hour autonomously on Route 28. So it was a huge advance in terms of being able to process camera data in a way that could be used for robot control. And this funny looking diagram over here is interesting too. This is the set of learned weights of the network for one of these units. So when the system is trained, now you give it any image you want and it outputs a real valued vector. And then you, again, pick the value that's largest and say, well, that's the direction you should steer. But if you want to know what these weights are representing, this is actually a diagram of all of the input weights to one of these hidden units, where the weights are mapped out in the same, in their locations on the image. And a white big square means it's a high positive valued weight. Gray square means it's close to 0. A large black square means it's a big negative weight. And so you can see that the weights that were learned from the different locations in the image to the hidden unit had kind of an interesting pattern that almost reminds you of a road disappearing into the distance. And this is the set of weights going out from that unit to each of the final outputs of the network. And you can see here that when this unit is activated, it assigns a large positive value to these nodes over on this side and big negatives to over here. So basically, if this thing is activated, it's recommending that you steer to the left. And if you think about that, maybe that's because if the road is lighter than the background, it's activated if the light stuff is over on the left side of the image, which might then make it a good idea to steer left. Yes?
Just a guess, but shouldn't they be symmetrical?
You think this weight diagram should be symmetric?
Just in case I'm asking. If the road is straight, shouldn't it be symmetric?
Well, let's see. What you're trying to learn, I think it should not be. What you're trying to learn is a function that will take any image as input and then output this kind of peaked value in the direction you should steer. And you have several different units to do this. Each of them actually has a different weight diagram. We're looking at the weights just for one of those 4 hidden units. And so if you actually look at them all, what you see is that some of them are activated, especially when the road is over on the left, like this one. And it recommends, if it's activated, it's going to, because of its outgoing weights, it's going to effectively activate these units. And then there will be another one that might be active when the road's over on the right. And it might have weights going out that activate the steering command to turn right. Might be a third one that captures the center. And there could be all kinds of weird combinations of those too, right? It can be factored into all kinds of not easily interpreted ways.
So where did it come
Yes, and then yes?
from? So it's only controlling the direction of the steering.
In this case, it's only controlling
So
the,
what if there's an obstacle, like another car in front of you?
right, it would just crash right into it. Which is why nobody was talking in the public press about autonomous driving in 1993. Things have come a long way.
Do you know how they chose the architecture? What is the process? Like how did they find 4 in the middle and 30 output?
Yeah, we just discussed that right before you came in. Okay, so I want to use today to cover a lot of a broad swath of what's going on and dive in a couple places that I think are particularly illustrative. But here's one set of ideas that kind of motivated people in the 1980s when neural networks kind of started being developed. One of the ideas was that, well, the brain is an example of something that computes pretty well and learns pretty well. What are some of its properties? Maybe we should be looking at computer organizations, architectures that mimic that. And so here's some just facts about your brain and mine. Your neuron switching time is about a millisecond. That's about the fastest that your neurons can change state if something happens. You have about 10 to the 10th neurons in your head. Each of those neurons has about 10 to the 5th inputs coming to it, synapses that connect it to other neurons. And if your mother walks into the room, or I show you a picture and your mother is in there, it takes you about 1/10 of a second. That's about as fast as you can recognize your mother or anything that you're familiar with. And therefore, you can, by simple arithmetic, notice that you recognize your mother with 100 inference steps. Your neurons aren't going any faster than a millisecond. So if I chain together 100 of those, 100 of those, I get up to 1/10 of a second, which is your mother recognition delay. So it must be that the brain is doing something that's not very deep. It's 100 steps, which is very small compared to the 10 to the 10th neurons that you have. And so it must be that there's a lot of parallel computation going on. And in fact, we know there is from various neurological studies. But this was taken as kind of motivation for why we might want to look at artificial neural networks by designing systems that have many neuron-like threshold units connected in a way that's very wide and somewhat deep, but not millions of neurons deep. Okay, so that was kind of one of the overarching guiding ideas that was floating around at the time. And so then that led to this idea, well, let's build them out of these sigmoid units, as we just discussed. But here you can see I've drawn one under the microscope. The inputs over here on the left are a vector of real valued inputs, x1 through xn. A weighted linear combination of those is computed, and then it's passed through the sigmoid function, giving us effectively the same function we use for logistic regression. And that's the standard sigmoid unit. It turns out there's one very nice property that made people like using this, which is we're going to end up training these with gradient descent, just like we train several other algorithms we've talked about. And one of the nice things about these sigmoid units is that the derivative of the sigmoid function is very easy to compute. If we take the sigmoid function, which is this function of x, its derivative is just its output times 1 minus its output. So it's very easy to get the derivative of the sigmoid unit. Before we talked about gradient descent for linear regression, for example, and you remember it was pretty easy to derive the gradient for linear functions. Here we're taking a sigmoid of a linear function, and by the chain rule, it will turn out it's very easy to get derivatives for this too. So this is a kind of nonlinear function we can use for which we can still very easily calculate gradients. Makes it nice to train. So that was actually one of the motivations, if you ask, why not use some other nonlinear function? We like to have threshold units whose gradient is easy to compute, so we can use gradient descent to train them. Okay, so given that, if I ask you how would you train one, suppose I have some input x, I want to predict y, and I have a neural network I want to train to do that. We could go back to our old model for real valued regression, say linear regression. Remember, we talked about if we make the modeling assumption that the output we observe is the result of some deterministic function of the input plus zero mean Gaussian noise, then we already talked about the fact that the maximum likelihood estimate would be simply the one that maximizes the log conditional probability over each of the training examples of the output for that training example given the input and the weights that we're learning. And then we derived before in class that, doing that under this model is equivalent to just minimizing the sum of squared errors. So that means if we want, if we want to train our neural network to have maximum likelihood estimates of all of those weights, all we have to really do is train it to minimize the sum of squared errors. That is, over each of the training examples, minimize the sum of the difference between its predicted output and the actual training example output. So this is just rehash of our earlier real valued regression. And similarly, we could do map training too if we want. Remember, then we decided we put a prior on our weights, let's say a zero mean Gaussian prior, which then turns our optimization problem into maximizing this quantity. Again, there's a data likelihood term plus the prior term. And if we work that through, then just like in the case, I'm losing my voice. Just like in the case of linear regression, it turns out the thing we want to optimize is just the sum of squared errors plus this regularization term that penalizes weights that have big values far from zero. Okay? So it's the same story we saw before with regression. It's just that now if we want to actually implement a gradient procedure to optimize these things, it won't be exactly the same as the gradient for linear regression. we're going to have to come up with a gradient for that complicated neural network, which is sigmoid functions of sigmoid functions. Well, it turns out that's not that hard. So here, suppose we just have one unit like this, and we want to minimize the sum of squared errors. That means we want to know the gradient of our error, which is with respect to each of these weights in the network. And if I say D is my training data, then what I really want, the error is just the sum over those training examples of the difference between the target output that we want our unit to output and the input vector, xd. I'm sorry, xd is the input, but we want to minimize the difference between the supervised labeled target output versus the observed computed by our unit output, and minimize the sum of squared errors there. So the steps are not too hard. Remember, you take the derivative of something squared by taking 2 times its derivative. And then since the weight doesn't influence the target value, only the calculated output of the network, the derivative of this is just this. And then we can, if I define net to be the linear sum of the inputs, the weighted linear sum, multiplying each of those by its individual weights, and then the output is the sigmoid function of that, then the chain rule lets me decompose this into those 2 steps. And now we can take advantage of that nice property I mentioned about the sigmoid function, that its output is, its derivative is just its output times 1 minus its output. And so eventually that gives us this very simple formula for the gradient of the squared error with respect to weight wi of the unit. So that's it for a single unit. It's a little more complicated math, but it's no more conceptually difficult math if I have a network of these. And if I do, that leads me to the following algorithm. So here's what turns out to be a gradient descent algorithm for training neural networks, even if they have multiple layers. The algorithm says you keep looping. Each loop through here, you're taking one gradient step. And on each step through, you go through the examples, you input them to the network and see what the output is. You calculate this quantity for each output where t is the target value, the label that you have. O is the value computed by your network. And so this is an error times the derivative of the sigmoid function. And then for each of the hidden units, those intermediate level units, there's an update rule that you can see I was looking for the place where this would get connected to my update. My update is I'm going to update each weight from unit I to unit J by adding to its old value some update. And that update is going to depend on a learning rate, the input to the ith input to that, the update for weight from I to J will depend on the value of the ith input and this delta term that we're calculating here. And these delta terms are effectively, at the output level, they're just the actual observed error. But at the hidden unit level, they're this quantity, which is really, so for the hidden units, the middle layer, instead of having an observed error, it turns out we have this quantity, which intuitively is like sharing the output errors in proportion to the weights that go from this hidden unit to that output. So the whole thing just kind of, if you look at this for a while, it makes very intuitive sense. But if you work out the math, you see this is exactly the gradient descent rule that you get if you say my function is this complicated multi-layer composition of sigmoid functions. But the bottom line is that this is a pretty easy algorithm to implement and pretty efficient to calculate the gradients. And so this is the standard back propagation algorithm for training multi-layer uniform networks of sigmoid functions, sigmoid units. Okay, and before we talked about gradient descent, we talked about the fact that you can do it in the batch way, which is what we just saw, and that if you're in a hurry, you can also use what people call incremental or stochastic gradient descent, where instead of calculating the gradient with respect to the entire data set and then doing an update, you can instead calculate the gradient with respect to just one data point and take a smaller update. And you can prove that if you make the step size of your update small enough, as that step size approaches 0, then the sum of the individual data point gradients approaches the true gradient. But in practice, this turns out to be a much faster way to train things. And it's by far the dominant mode for training these kind of networks and the deep networks that we'll talk about in a few minutes. Okay. So stochastic gradient descent, another theme that we've seen before, returning here. Okay, so in practice, how does this work out? Well, if you train a network, you often have to train it for thousands of gradient descent steps. Yeah?
I'd like to discuss if I can. So the function that we're trying to optimize, is it convex? What can we guarantee about this?
Ah, right. Yeah, the function we're trying to optimize is absolutely not convex.
Right, so therefore,
Right? This network is a very nonlinear thing that can have a lot of different local minima, local optimum. And so when we try to minimize the sum of squares of squared errors, we will find through gradient descent, we're guaranteed to find a place where that error, sum of squared errors, is locally minimized. But there could be another part of the weight space where we could get a much better optimum. And with gradient descent, we're only guaranteed to find one of them. And so there are a lot of engineering tricks of the trade that people do, like, for example, initialize the network with weights that are small random numbers close to 0 and train it, see how well it does, then redo. And each time you randomize, you set the network up initially with different random initial weights, hoping that eventually, if you do this enough times, you'll find a really good local minimum. In fact, for many years, in a nutshell, the history of neural nets is that they were very popular in the 90s, partly because of Dean Pomerleau's success driving on Route 28 and other similar successes. And then in the late 90s, they fell out of favor. They fell out of favor partly because people didn't like the fact that it was hard to characterize what they were doing and it was hard to train them, and you have all these local minima problems. Recently, they've fallen into favor, again because, just like in the case of Dean outperforming the current state of the art, deep networks today have outperformed the current state of the art in computer vision, speech, and lots of other areas. And so they're in favor again. And part of the reason they're in favor now is that, and people are now coming up with more principled models of neural networks, which I hope to get to toward the end of the class. But anyway, there are all kinds of problems training them, and you see one here. So for example, here's a training of a network. Here you see the error plotted this way, and I'm plotting both the training error, which is this monotonically decreasing function. Of course, it would have to be monotonically decreasing function as we increase the number of gradient descent steps. It's the definition of gradient descent. It's guaranteed to monotonically decrease the training error. Here you see the test error, the error on a held out set of test examples. And here you see a plot for a different example. So up here you can see the usual kind of overfitting curve, right, that we see in many cases, the top plot, where the training error keeps getting lower, but at some point the test error starts rising. And we know that the network has overfit the data here. And so which network would you like to use for the future? If I write out every one of the networks that I get along the way as I'm training different numbers of gradient descent steps, which number of steps would you want me to, which of those networks would you want me to use in the future? Yeah, the lowest one, the one that's about here at about 10,000 gradient descent steps. And so this plot actually illustrates one of the reasons it's difficult to pick the right number of gradient descent steps, because here you see again the training error monotonically dropping, but the test error drops and then actually it rises. So if we were short-sighted, we might say, okay, stop there and let's use this network. But in fact, if you keep training, you actually do better. So it's not, it's not a simple matter to choose the network.
So this is for a fixed topology, right? But how do you choose a topology?
This is
For a fixed topology. For a
fixed
network,
topology.
How do you choose a topology?
The topology in these cases, and in the early days of neural networks, even today, is you fix it in advance. And these are uniform. You saw the completely connected structure that we're using.
How many units in the middle? Like how many layers? How many?
Oh, how many layers? This is 2 layers, which is very standard, and completely connected. Every one of the inputs is connected to every one of the nodes at the next layer, and then onward, just as we saw in the pictures I was showing. And that's kind of the standard backprop. There's a reason for that, which we'll get to. Okay, so what can we say about artificial neural networks? Well, here's some things that are true. If you're an engineer, you probably know that you can represent every Boolean function with a 2-layer deep circuit of NAND and NOR gates. And there are various basis sets of Boolean components you can use to build Boolean circuits. That result generalizes to sigmoid functions. Sigmoid functions can represent AND gates with the right weights. That's a good thing to do in the shower. Figure out the weights that would represent an AND gate with a sigmoid unit. Also, they can represent a NOR gate. And so it turns out that every Boolean function can be represented by a network, completely connected network, with just 1 layer of hidden units. Input, hidden units, and then the output, like the ones we've been looking at. But it might require an exponentially wide hidden layer, depending on the Boolean function. In the worst case, exponentially wide. We also know some things about continuous function. Every bounded continuous function can be approximated with arbitrarily small error, again with a network with 1 hidden layer. And even if it's not bounded continuous, any function can be approximated with arbitrary accuracy if you have 2 hidden layers instead of 1. So these results actually justify using not very deep networks, at least in terms of the representational capacity of the network. It can represent a very diverse set of functions with these networks, shallow networks of sigmoid functions. Okay. But let's look at what really happens in here. This is actually to me, this is what got me most excited about neural networks when I ran this little experiment. So here's the network, very simple network. Again, 2 layers. I drew it on its side. The inputs come in from the left, they go out to the right. What do you think would happen if I train this network with these 8 training examples? Notice each of these training examples, I'm giving an input with all zeros and a single 1. And I'm requiring that it train itself to produce the same output. Produce the same input that it was given as its output. But of course, it has to do it with this network structure. So who thinks that this will be trainable? Who thinks it won't? So when you train this, here's what happens. It's successful despite the fact that I'm asking it to encode a bit string like this also at the output. But if you look at the training examples that I gave it, there are 8 possible inputs and the same 8 possible outputs. When you train this network, it learns a collection of weights so that after it's trained, if you input this vector, the values at those 3 hidden units are 0.89, 0.04, and 0.08, from which it reconstructs this output. And here are the hidden unit values for the others. So what I like about this, you see the regularity? Very cool. This is the Boolean code for 1 of 8. If I give you 3 bits to encode 1 of 8 possible items, you'll get exactly this Boolean code if you just round these numbers up or down to 1 or 0. So this would be 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0. You get it? So the network, because it's being forced to minimize the sum of squared errors between the outputs that I want and the outputs it's producing, is being forced, even though it's not aware of it, to come up with an encoding of the input values that allows it to reliably produce the outputs that I wanted. And even though it's not aware of it, this turns out to be basically the bitwise Boolean code for 8 items in 3 bits.
So could the encoding view of the hidden layer also apply to a continuous variable for example?
Yeah. So I'm discussing this as though it's a binary code. It's actually a continuous code, right? So I like this example because it makes it easy to see that neural nets can be very interesting because they can learn representations. And your point is right on target. Actually, they're even more interesting than learning Boolean representations. They're actually learning continuous representations, continuous feature vector representations of the input. And what property do those representations have? Well, they have the property that they're computed from the input and they contain the information needed about the input to calculate the required output. So this is actually the reason why neural nets are a big deal in the last 5 years. People have figured out how to take this property of neural networks of learning representations that are useful and make it really effective across a variety of applications like computer vision, speech recognition, machine translation. Yep?
So if you only have 2 points at the hidden layer, can you also learn the same results?
If I only had 2 hidden units instead of 3, who thinks it would work? Who thinks it wouldn't work? Okay, somebody who thinks it wouldn't work, tell me why.
I'm thinking that 3 bits can represent 8 results, but 2 cannot.
Right, it's certainly true that you cannot encode 8 values with 2 bits. But I think it could work, in principle, to encode 8 items into continuous numbers. In fact, all you need is one continuous number to encode 8 items. So the real question is, but could that code be calculated as a sigmoid function of the inputs? And that I don't know. Now I'm out of my depth. And would the gradient descent process actually converge on it? That's another question. Okay, so your question is a good one. And if these were bits, then I would agree with you that 2 would not be enough bits to code 8 items. But the fact that these are real valued actually makes the situation even more subtle. Yep?
After we train this network with these examples, what happens if there's like 2 ones and the rest of the ones?
Right, I don't know what will happen, I mean, surely it'll calculate something no matter what bit string we put in.
Can they expect it doing that? The same thing as that?
Yeah, I didn't run that experiment, but this would be a great thing to try. If anybody tries this, bring it in next time, and we'll give you 2 minutes at the beginning of class to show us what it does. It's easy to train this. Okay, so I want to move ahead because I want to talk about some other examples. Let me quickly talk about this one too, because it kind of illustrates even better the idea of continuous representations. So here's another very simple network. It has picture as input, 30 by 32 grid of pixels, only 3 hidden units, and then 4 outputs that are meant to classify the image according to whether the person is looking to their left, straight ahead, to their right, or up. And you can train this network with backpropagation, the algorithm we talked about, and it will do quite well. But now, what is the code that you think gets learned there in the middle? Well, we can again we can visualize this code by again looking at the hidden units. So let's look at this hidden unit. We could look at what it's encoding by looking at the weight values from each of the input pixels to that hidden unit. Those weight values are shown here. And for this hidden unit, those are the weights. And for this hidden unit, those are the weights when we display them in the same location where the pixels would be. So you see these kind of weird ghostly face-like displays of weights. And these weights here show the weights coming out of that hidden unit to the 4 outputs. So for example, or I'm sorry, these are the ones going into each of the 4 outputs. So, you know, if you look at this, you might start seeing things like this one in particular seems to have a lot of dark here and a lot of light here. If a person's looking that direction, there's going to be dark stuff in this part of their image and light stuff over here. And that one would probably be activated more because it'd be multiplying negative numbers by negative numbers and positive numbers by positive numbers, so you get a big activation. And it's item number 4, and so the output weights from this to these are, I'm sorry, it's item number, yeah, it's item number 4. The first weight is the 0 weight. So this one actually has a large positive weight to the straight output and a large negative weight to the looking right and a moderate weight to the looking left. Okay, so you see it's not easy to understand what these things are doing, but you also see that they can come up with quite interesting representations.
So based on the dimension of inputs, do we have a bound at least how many hidden units we need to?
Yeah, that's an experimental thing. There's no easy way in general to say how many hidden units you need. It's typical, like a good engineering rule of thumb is for any problem you start with, try half a dozen hidden units. and with these kind of networks. And if you're not happy, then try doubling that and see if it makes a difference. But no, there's not an art, there's only an art. There's not a science to choosing the number of hidden units. These days, people have, in more modern, in the deep networks, some of them, people use actually thousands of hidden units, but use training procedures that impose sparsity constraints on the codes that get developed in the intermediate layers. And so that seems to be quite successful in many cases, to use very wide hidden units and sparse codes. Yes?
Is there like a measure that if we increase the number of hidden nodes by say X amount, the accuracy will go by this much amount? Is there a rule? If we increase the hidden nodes, accuracy goes up or down, say.
Yeah, you could think of, I guess if you think in terms of something like VC dimension of the neural network, you could imagine that if you had too few units, it might be hard to represent certain functions, and if you had enough hidden units, then it would be
Is it dependent on the number of input variables?
yes. So it's a complicated thing, and I actually don't know whether people have, I remember seeing some work on trying to analyze VC dimension of neural networks.
There is the book by Peter Bartlett and Martin Anthony at the late 90s. They worked out. I can find the book.
Yeah. So there is a book, I'm being told, on analyzing sample complexity for neural nets.
No, yeah.
Peter Bartlett.
And Martin Anthony, yes.
Yeah. So there is work in that area. I'm not sure sort of how far it has progressed, but if there's a book, it must, there's at least a lot of energy there.
I do have a question actually here. So this is face detection.
Is this face detection?
What is that?
This is face pose. So the outputs is this person looking to the left, right, straight, or up.
My question would be, so I guess at the late 90s, people, that means like other boost or other techniques like SVM did better than these neural networks, right? And what was the reason? Because of, computational power, like not...
Well, let's see. People have demonstrated, for any algorithm, people have demonstrated that it outperforms all other algorithms on face recognition.
Sure, but I think that like Viola and Jones or like, so definitely, okay, I think it's fair to say that's why they went out of fashion, right? Like,
Right.
like other boost or SVM or doing at least as well as neural networks.
That's right. So support vector machines we're doing at least as well as neural networks because they also work in a nonlinear space, right? Through the kernel functions, we can make very nonlinear classifiers with support vector machines. So kernel methods were one of the things that overtook this. And things like AdaBoost also have a way of building sort of arbitrarily complex combinations of things. The current state of the art is actually neural networks again. So the very best techniques for face recognition are now deep networks. So networks, but not this particular architecture.
Okay, and the question is why? Because
And the question is,
so there's no computational power now, or why? So why are they coming back? And why do they do better than the competitors?
right. So that's a complicated question. I want to answer it with slides instead of on the fly. So let me skip over a little bit here. Okay, so now modern neural networks are kind of a extension of this idea in several important directions. So one direction is people have come to realize that you don't necessarily want to use a graph topology for your network that's homogeneous and uniform. And people have gotten good at designing specialized topologies for different problems. For example, for computer vision and for time series data and so forth. So let's look at time series networks. Suppose, for example, we want to train a network to predict some time series. It might be a robot driving around with cameras, and we want to predict if it takes some action, what will be the next state of the world. Or We want to anticipate the next word in a sentence. We're a speech recognition system, and we hear, I dropped my phone on the, we want to predict the next word so we can anticipate it and do a better job of recognizing it in the midst of noise. But we might say this is not a Markov system. That is, our prediction of the next word in the sentence might depend not just on the previous word, might depend on all the words that were in the sentence. I dropped my phone on the, not just the, and now predict the next word. So we'd like to have a way of predicting, of training neural nets to do this kind of time series prediction. One of the specialized architectures that people use called recurrent neural networks. And here's the idea. If here's a typical neural network, well, I could input the input value at time t and try to predict something at t plus 1, time t plus 1. But if this is just an encoding, say, of the current word in the sentence, and I'm trying to predict the next word of the sentence is my output, if I want to actually use the history of words in my sentence, then people use a recurrent network that has this structure. The way you understand this is that at any given point you input your observed x of t and you predict your output. But you also add one or more other units that are also a function of the current input, and that become an input at the next time tick. So if I calculate b as a function of x of t, I'm going to make that an input when I put in x of t plus 1 to predict y of t plus 2. So this is a way of saying this unit, its job, and the learning procedure has to figure out how to make sure this happens, but its job is to summarize the previous input in some value, and this could be multiple nodes, so it could be a code for the previous input. So that now I'll input x at time t, but also this context at time t, which is summarizing the previous input. See what I'm doing here? Okay, now actually if you look at this network, it's not summarizing only the previous input, it's an arbitrary history of inputs, because let's call this the context at time t. Well, it's also an input, and so the context at t plus 1 is going to be a function of the current word, let's say, plus that historical context that got calculated previously. And so this context becomes an arbitrarily long, this can encode arbitrarily long histories of the inputs. And it's going to influence, again, these values as well as the next context. So it'll influence the classification problem I'm trying to do too. Okay, so this is an example of a specialized architecture designed to capture the idea of time series prediction, and that we want to learn a representation. I'm showing it just with one node, but it could be many. We want to learn a representation of the arbitrary past that's going to be useful for the classification prediction problem that we're trying to do. And if we can come up with a training procedure to do that, then this will be a useful thing. Well, it turns out the training procedure is actually trivial. All you have to do is use the backpropagation algorithm that we already know, but you have to transform things a little bit in the following way. Suppose I effectively unwind in time. So here's my x2 at time t, my x at time t minus 2, and the value of the context vector that I have at t minus 2. It will then produce a context which I will use at t minus 1, which will then produce a context which I will use at t, and so forth. So I can effectively make a second neural network by just reinstantiating that one and unwinding that feedback loop in time. And now I have a standard loop-free neural network. And it turns out that back propagation algorithm, the stochastic gradient descent algorithm that we talked about, easily applies to this kind of directed acyclic graph. And so I can basically train this network, and then I want to fold the results back together. So what I want to do is I want to make sure when I'm done that this unit and this unit don't have different weights. These aren't different weights. I want them to be one weight in the final network. And similarly, I want, this and this to be the same weight in the final network. So I can unwind it, but as I'm doing the stochastic gradient descent, on each step, when I make an update to these different weights, I force them to share the parameter. I force them to share the same weight. So I'll update these, and they might get different updates in this unfolded network. But in the end, since I want them to be one thing, I take the mean of their values after the updates, and I assign each of them the same average of their updates. So this illustrates two ideas, which are now rampant in the field. One is designing a special purpose structure for the network to fit the problem at hand. The second idea is parameter sharing. Parameter sharing meaning that when I update this unfolded network, in the end, I'm not allowing this to really be a distinct weight from this. I'm instead enforcing the constraint that this weight must equal this one. And my gradient descent procedure gives me a way of, it treats these separately, but my update step enforces that this parameter and this parameter have shared value. That's a very powerful idea too. It's widely used in something called convolutional neural networks, which are widely used for computer vision, where you want different image patches to be analyzed locally, but you want the analysis to be invariant of where that locale is. And so you want to share the parameters. Okay, so let's move on. Speaking of convolutional neural networks, here's another specialized architecture, which is very popular in computer vision these days. This is a diagram of a much deeper neural network, which differs from our standard architecture in a couple ways. One is in the first layer, each of the units really is sensitive only to a local patch in the image. So it's shown by this black rectangle. And there could be rectangles overlapping, scattered all over the image. Each of those is used as the basis for computing a value in the first layer. Okay, so it's a specialized architecture that has restricted field of view for each of these nodes. Then there's the second layer, which does something called max pooling. That is, it calculates a different function from a sigmoid function, where it looks at a particular collection of these units that are associated with some slightly larger region of the image, and it takes the largest, max pooling, it takes the largest out of the pool, and it outputs that value. So it's again a nonlinear threshold unit, but very different from the units that are used in the first stage of the network. And then actually this is another layer just like the first one, and another layer just like this one. And these different, for example, the field of view here is larger than the field of view in the first layer. And so as you go deeper into the network, you get increasing fields of view influencing the value of any particular unit in the image. Why would you want to do that? It works. But it also turns out to be true of primate visual cortex. So it also turns out that if you go in and measure neuron firing in monkey brains, you see that in early visual cortex, the neurons are sensitive to very local patches in the image. And as you move further up cortex, you see neurons that are functions of much wider patches of the image. So part of this is motivated in a loose way by what's known about primate vision, and part of it's motivated by just engineering and trying things and finding out what works. But the net effect is this another kind of specialized architecture that mixes different types of unit. It's not completely connected, and it's motivated loosely by primary visual cortex. Again, there are many shared parameters, just like in our recurrent neural network. Here the sharing happens, for example, at this level. These convolutions, each point gets a different field of view in the image, but the weights that are used to analyze that rectangle are the same for this rectangle as they are for every other rectangle. So there, again, there's a parameter sharing going on. And this idea of engineering your own architecture for the problem at hand, recurrent neural networks, convolution networks, is now very popular, and there's a lot of innovation going on in this area.
So what's the intuition in these convolutions and pooling? Has something to do with the visual data?
Yeah. So this seems, like a very reasonable thing to do for visual data. If this was a speech signal and I happened to represent it as a matrix by winding time like this, you might think that's not such a smart engineering thing to try for what's effectively a time series. And so people have developed other specialized architectures for speech and so forth. So there's a lot of it is trying to understand the character of the data, try to understand what kind of stages of processing you would think might be relevant and helpful, trying to understand the noise characteristics of the data.
So maybe you are trying to, with convolutions and pooling, you are trying to capture somehow some invariances to translation or whatever, what are you trying to capture?
Yeah, that's right. So that's right. Translation invariance that's a great point. So if you think about this architecture, it will give you kind of for free translation invariance because of this parameter sharing that's happening at the first part of the image. Or something like that. You'd also like rotation invariance. And in fact, there were some earlier precursors to this where people explicitly built into the gradient descent function in the earlier types of totally connected neural networks, built into the objective function being optimized by gradient descent, additional constraints to try to capture translation invariance, rotation invariance, scaling invariance. And here it goes to the architecture instead of to the objective function. And I think the jury is still out. People are doing actually both kinds of things these days. But the big advances have really come from engineering the architecture rather than the objective function, interestingly. Okay, so let's talk about deep belief networks. So this is another species of artificial neural networks, which is very popular these days. Unlike the ones that we've been talking about to date, they're often trained not to do a classification or a regression function, but simply to be an autoencoder, just like, that is, to produce as output the same thing that we saw as input. In the same way that, remember the bit string with that came up with the Boolean code, that's an autoencoder, people use that term, to mean that it's just a network that's supposed to produce at its output the same thing you gave it as an input. The identity function is not a very exciting function to try to learn. But the reason to do it is to get the system to learn an interesting code, like we saw, for that type of data. And so deep belief networks replace our simple earlier example with a much more deep, many hidden layers of units. And this is also a very active area of research right now and leading to quite interesting advances in terms of engineering useful representations for different types of data. So let's take a look. This example is taken from a paper by Jeff Hinton and Ruslan Salakutinov. Here's what they did. They trained an autoencoder which over images. So you input an image, it's supposed to output the same image. They had a hidden layer first of 2,000 units. You're asking how many units to use. Then they followed it by 1,000 unit, and then a 500 and a 30 and a 5, and then it went back out to recreate this. Furthermore, they trained it so that these weights and these weights are the same, these are the same, these are the same, these are the same. So there's parameter sharing going on. And up top, you see some examples of images that were input and the images constructed as outputs by this trained network. So you see it's doing a pretty good job. Not perfect. Like in this one, I think it kind of missed the glasses, right? But it at least captures the nose and many features, the orientation a little bit. This third row is interesting too. This is principal components analysis output. Remember principal components analysis from the other day? Principal components analysis, what's that again? Right, that's a way of learning a linear encoding. Right. So PCA is a way of finding the dimensions of greatest variance of the data. So we end up with an orthogonal basis set that can be used to then reconstruct the data once we know the coordinates in this basis set. That's like saying, so if we give it images, what's it going to do? It's going to find each dimension of PCA is going to be a face-like vector, and linear combinations of those different face-like vectors will correspond to the coordinates of the PCA vector, and then the linear combination of those according to their coordinate values will be the reconstructed face. Okay, so it's like this with linear units. And with a constraint in PCA, they happen to be an orthogonal basis. Here we have no guarantee that it would be orthogonal. Okay, but what's interesting is if you compare this deep network reconstruction of the faces to the 300-dimensional linear PCA, you see that even though it's only allowed to use 30, a vector of dimension 30 instead of a vector of dimension 300, its reconstruction of the face is actually somewhat better. So here you see the benefit of going nonlinear, basically. PCA is restricted to be linear transforms. Okay, so how do they do this? Well, here's how they did it. The big problem with training deep networks is local minima are rampant and it takes forever. So here's what they did. I'll just read you the figure. They said pre-training consists of learning a stack of restricted Boltzmann machines, each having only one layer in it. So they learn weights that map from the face to a 2,000-dimensional hidden layer and back to reconstruct the image. Then they take those, they freeze these weights, and when they input an image, they just calculate what are the 2,000 hidden values. And they train another one that forces encoding those 2,000 values with only 1,000. It's a completely separate training problem. Once they get that, they take the 1,000 and they force training completely independently another network that has to reduce that to 500. Okay, so that's the pre-training. The learned feature activations for one of those are used for the data to train the next one in the stack. After pre-training, these are unrolled this way to create one single deep autoencoder, where again these parameters are shared. So this matrix of weights W2, the transpose of that is used to do the decoding. And then it's fine-tuned in the end with backpropagation, our original algorithm. Okay, so it's kind of an engineering blend of different ideas. But this is the kind of thing that you have to do if you really want to train successfully a network that has a very deep sequence of hidden layers. If you just try to train it with our standard backpropagation, it doesn't work very well because of local minima, and just takes a long time for the gradient to update these early stage weights. You have to first update all the other weights, and it just doesn't work very well. So this is one of many. There's now an industry of variants of deep networks. If we had another whole lecture on this, the next thing I would do would be to talk about restricted Boltzmann machines. Why? Because that's a variant of these networks that has a very nice probabilistic interpretation. So far today we've been talking about these units as being real valued things that are used to compute more real valued things, and they are. But there's a very nice interpretation of restricted Boltzmann machines where you say each of those hidden units is actually a Boolean random variable. And the continuous value of that unit is actually the probability that that Boolean random variable has the value 1. And then we can think of these networks as actually capturing joint probability. These autoencoder networks then can be viewed as ways of capturing, of modeling the probability distribution over the collection of image data that they're being shown. So they become kind of density estimation or probability. It's like we're showing samples of some set of inputs X, and it's learning P of X. But the form, the parametric form of that probability density is determined by the architecture of the network. So there's much more to be said about neural networks. We should have a class on neural networks soon, I guess. But I think the key things for today, see, I could give that whole thing on restricted Boltzmann machines. No. So I have way too many slides in this thing. Okay. Let's just say, never mind. Here's what you should get out of today's lecture. Neural networks are cool again, but for good reasons. The good reasons are they really have moved forward the state of the art in several areas people have worked long and hard on. Computer vision, the best techniques these days for training image recognition systems are by far better are neural network approaches. They dominate the earlier winners, which were support vector machines and other techniques by very substantial margins. Also in the area of speech recognition, they're making huge differences. In both cases, the image and the speech recognition cases, the reason that they're making such big impact is because they're able to learn these nonlinear encodings of the types of data that are being used that are pretty noise resilient. If you think about it, if you have a lot of data of images and they're all noisy, and you force me to learn an encoding and I can't predict the noise, then my representation encoding that I'm going to learn is going to have no choice but to capture the signal and ignore the noise if it's unpredictable. And so a lot of these learned representations are actually quite robust to noise in the image. They can do some amazing things like complete the second half of an image if there's an occlusion over part of it. And so a lot of the advances really come because these techniques are very effective at learning of representations. And once you get a good representation, then you can train a classifier to work off that. Could be a neural net classifier, it could be a logistic regression classifier, it could be a support vector machine. But learning representations is kind of now a hot topic, and I think deservedly so, right? A lot of machine learning has been about function approximation. How can we learn functions? But to learn very complicated functions, you have to have the right representations. And up until, let's say, 10 years ago, all of the work, even 5 years ago, all of the work in, say, image recognition involved very clever feature engineering. Things like SIFT features and other kinds of libraries of features for encoding image properties that you would apply as a pre-processing step, and then train your classifier on that featureized encoding. But now what these networks are allowing people to do instead is just use the raw pixels. Don't bother using the SIFT features. Just use the raw pixels and force the network to learn the encodings. And that's actually where a lot of the benefit is coming. Okay, so more to come next week. Oh, there's a homework assignment out or coming out very soon. Don't miss it.